welcome back. We are on to lecture 33 now, and let me begin with a quick recap. Last time we looked at Gallagher's decoding algorithm A, where we looked at density evolution, and then actually proved a statement that I had made earlier. Completed proof showing that assuming a check node variable node and channel output symmetry, one can assume for the purpose of estimating error probability that the all one code word was transmitted. And today what I would actually like to do is, so the title of our lecture today is more or less the same as the title last time. We did not quite get to belief propagation decoding. So, BP here stands for belief propagation. So, we did not really get to belief propagation decoding of LDPC codes. So, what I have done is I have carried over the title. So, let me just make sure that I give this lecture a title. Okay, very good. So, what do you mean by belief propagation decoding? And I am going to actually, so I want to tell you first of all that belief propagation decoding is no different than the method of decoding that was employed on the junction tree. Okay. So, I would like to bring that back and then we will continue our discussion. So, let us see if I can pull that up from one of our previous . Okay, so this will actually suffice, although I may have another lecture which describes the okay. So, let me just pick this particular page, put it into our current lecture. Okay. So, let us assume, so this is our 742 code, block code that we had actually looked at earlier, which had associated to it a certain parity check matrix. And let us assume that we are back in which we posed the decoding problem, the maximum likelihood code symbol decoding problem as an MPF problem, and then we proceeded to actually solve it using the GDL, right. Now, we know that in the GDL you first organize the local domains into a junction tree, and then after you have the junction tree, then your next step is to actually pass messages on the junction tree according to a certain schedule. Okay. And let us assume that for the time being we are interested in computing, let us say we are interested in the single vertex problem of the GDL, in which case we would orient all the edges towards that particular vertex. And at the end, after we have passed on messages, and also there is local kernels at every node, and eventually we would be interested in computing the objective function. Okay. The objective function, which in generic notation is beta 1 of x 1, but in our notation is basically a quantity that is proportional to p of x 1 given y, where y is the entire received signal. Now, I want to actually modify this expression slightly to reflect the fact that we are computing this probability based on the received symbols. Now, the other fact that this graph takes for granted is that this is computed assuming that you know the received signal, and also assuming that the 7 code symbols, original code symbols, were really drawn from a code corresponding to a certain parity check matrix. So, to emphasize that, let me just put the parity check matrix back here. So, this is the parity check matrix H of the code, and there are 3 parities, the parity corresponding to the first row, the second row and the third row. And when we computed this, this was conditioned computed taking this into account, right. So, to make that a little bit more explicit, let me just rewrite this and saying that this is p of x 1 given the entire received symbol, but also given 3 parity checks, which is chi A, chi B, chi C, where I am going to refer to this parity check as A, this is B and this is C, and I think I have done this before. And the quantity that we have computed is not exactly equal to this, but it is proportional, which for our purposes is actually good enough, is proportional to this. So, this is an objective function. Now, on the other hand, supposing, so we know what this message is, but if I stopped you at some point here and asked you, by the way, would you be able to tell me what is the message that is actually being passed here, that is from variable node 4 to this check node. Okay. So, let me copy this picture over so that I use that to make that point. Okay. So, this time let us say that my focus is on the message that is going on over here and not so much on the objective function there. And we already know that we are working with this particular code. but I ask you what is the message that's actually being passed across this barrier, across this edge. And it is not hard to actually show that the message that is passed here across this, and since I am going to be doing this a couple of times, let me do the following. Let me copy this page a couple of times over. Okay. So, across this what I am actually computing, you can show, is in analogous fashion what you are actually computing is P of x 4 given some evidence. So, this node is passing on its belief about x 4 given all the evidence that it has received. In particular, it has received information about y 3, y 5, y 6, y 7 as well as y 4, and in addition it also knows about the presence of these two parity checks. So, we can actually say that the message that is being passed is proportional to x 4 given y 3, y 4, y 5, y 6, y 7. It is also been given knowledge of the presence of these two parity checks. So, given this, it is passing on. So, what you might do is, and how do you, okay, now you might ask, well, how do you actually show that? So, if you actually try to formulate this as an MPF problem, and you try to just the way as we formulated the problem of code symbol decoding of x1 as an MPF problem, if you do that, then you will come up with a junction tree which is precisely the portion of the junction tree that is below this dotted line. So, this is what you will come up with, and you will find that then you are actually computing an objective function which is precisely this. Okay. So, that is a good way to look at it. So, if you want to actually see what is the message that is passing across any node, you can just isolate the part that is before that from which messages are being passed and say, look, I understand what this little network here is doing, because it is a junction tree set up to solve it. So, there is an overall junction tree, but it contains smaller junction trees, each of which is doing a similar computation. Okay. So, at this junction here, basically what you are doing is you are computing the probability of x 4 given the evidence, which in this case is y 3, y 4, y 5, y 6, y 7, and in a way the evidence, additional evidence that the 3, 4, 6 symbols satisfy parity, as do the 4, 5 symbols, and you can interpret this as a belief. So, this can be regarded as the current belief about the message symbol x 4. Okay. So, that is what is being passed, and now let us look at another, just to make this, give one more example. Supposing I now were to stop you and ask you, well, can you tell me what is the message that is going across, let us say this barrier over here. What is the message that is going across from node B to node 4, and once again you can actually show that the message that is going across here, the message that is going in this direction like this, is your belief about x 4. So, it is P of x 4. What you are given is the evidence that you are given is y 3, you are given y 6, as well as you are given the fact that 3, 4, 6 satisfy parity check. So, again the message that you are passing has an interpretation as your current belief. So, once again this is your current belief in the probability of x 4. All right. So, now in this context we understand that the messages that are passed are being passed across the network have an interpretation as beliefs. Okay. So, that is clear. Now, we want to actually move on to talking about LDPC codes. So, let me just to give you a sense of the context, let me pull up our one of our early lectures on LDPC codes. Okay. So, now supposing we are now working in the context of LDPC codes, and I want to talk about the messages that are being passed and interpret them as beliefs. So, the question is, can I really extrapolate from what I saw in the junction tree to this more general setting, and I want to make that connection. So, here this is just to give you the setting. So, now we are let us say working with LDPC codes, and this is the tanagraph of an LDPC code. So, now what I would like to do is to say, supposing okay, I actually unravel the tanagraph, that is that I am passing messages back and forth from left to right and right to left in this tanagraph. Now, what I want to do is I want to actually view it, unravel this and get a better understanding of this. For this I am going to assume that now we went through some definitions about neighborhoods, etc. So, I am going to assume that the neighborhood of every edge to depth 2L is tree like. Okay. So, let us put that assumption down. And we are going to say that this is true to depth 2L. Okay. So, the if it is a, so the notation for this was n sub e for the L, and let us make that a directed, and then we would have a 2L. So, we assume that this is tree like. Now, I am going to, this edge could either be going from a variable node to a check node or a check node to variable node. In this particular instance, let me consider unraveling it from a particular variable node. And if you draw this out, so let me see if we have such a figure available previously. Okay, here is the figure I was looking for. All right, here we go. So, let me delete some of these comments that we won't need here today. All right. Now, I am thinking of this figure here, and I think we have done this before. I am thinking of this graph here as an unraveling of this. That is, I am looking at a particular iteration. Let us say I am looking at, so here what we have is in this figure you have a 0th iteration where you are actually passing messages from the variable nodes to a check node. Thereafter you start the first iteration, and this is the beginning of the second iteration. Okay. And in the second iteration, at the second phase of this, so each iteration has a phase, the first phase being when you pass messages from a channel node, from a check node to a variable node, and in the second phase where you actually go backwards from the variable node to the check node. So, here now I am interested in particular in the message that is going across, let us say over here. So, this is from a variable node to a check node, and let us pretend that we are looking at the second phase of the second iteration, right. So, the first phase actually started here, the second phase is that, and we will assume that the neighborhood is tree like, okay. So that all these of this particular edge is tree like, and I guess to depth 4, which means that all the nodes are distinct as shown here. Now, okay, what is the relation from this between this and what we have been discussing? What I want to actually say is that under the assumption of a tree like neighborhood, you can actually view this as a junction tree. Okay. In fact, it is a junction tree. It's the junction tree. In fact, not only is it a junction tree, it is the junction tree that you will end up if you are trying to actually set up the problem of code symbol decoding of this particular symbol here. So, okay, I said this is a junction tree. So, what is that junction tree computing? Let me just redraw that a little bit better first. The function that we are attempting to compute here is the belief P of x 21 given what? You are given all the received symbols y1, y2 all the way up to y21. You are also given all the check symbols ranging from A, B all the way up to chi sub I. Okay. So, this is the belief that you will actually compute, and in fact, I do not have to prove anything to you because it is already clear from the manner in which we actually discussed the junction tree for the block code. The only thing that one might want to point out is that this is a junction tree. Well, why is this a junction tree? Well, it is a junction tree because what I could do is that I can actually rewrite these check nodes slightly differently. Okay. For example, this check node over here, I can write it as the check node, and I will write it in red so that it stands out, 1 to 17, and this check node here is 3, 4, 17. Okay. So, now if you actually replace all the check nodes where I have actually introduced letters by these symbols, then you actually see that this is a junction tree, because now supposing you project onto the code symbol onto the variable 2, which stands for x2, then you can see that the projection is connected. Similarly, if you project onto 17, you will notice that actually this one here would be replaced by, so let us replace this as well. So, this would then be replaced by 17, 18, 21, and you would have this. And now, if you actually project this entire graph onto 17, then you will see that 17 will show up here, 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 and the projection is actually connected. So, the conclusion is that this is a junction tree. So, this is the junction tree. That one would obtain if one the problem of computing this quantity here as an MPF problem. Okay. So, what that means is that if in the tanagraph we were to pass messages, so this is important, perhaps I should have said this earlier. If in the tanagraph we were to pass messages in just the same way as we passed messages on the junction tree of our earlier example block code, then assuming that the neighborhoods are tree like, then you would have the same situation as with the block code, and the messages that you passed could be regarded as beliefs. Okay, so, I will write that down also. Hence, we can if we pass messages along the edges of the tanagraph in exactly the same manner as in the case of messages passed along the edges of the junction tree associated with the example seven 4 2 block code, then when edge neighborhoods are tree like, the messages passed along the edges of the tanagraph can be interpreted as conditional beliefs. Okay, so that was the point that I want to make. So this message passing, as in the case of a junction tree, is called belief propagation based message passing. Okay, so from now on we will assume that messages are passed accordingly. So then now let us take a look at the message in general that is passed at a check node. So belief propagation based message passing in more detail. At a variable node, let us say corresponding to xt, then you would first of all have an incoming local kernel, which would actually give you p of xt given yt. Now, let me just rewrite that slightly differently. I want to actually say that I want to view all the conditions as being representing some evidence, okay, and I will explain that in slightly more detail shortly. Then you have an incoming message here, which you can write as p of xt given E1, p of xt given E dv minus 1, and then you have an outgoing message, which is then p of xt given the union I is equal to 0 to dv minus 1 E I. Okay. And all your messages are actually there should be a proportionality constant included here. All right. So, hopefully from the discussion that I just told you, this part is actually clear. That is, every message that is being passed is actually because we saw that here, right. I mean, because we saw that let us take for example here, the message that was passed here was an indication about the belief of x4 based on these, right. At a different junction here again it was the belief about x4, but based on more evidence. So, the evidence here in this particular case for instance was based on received symbols y3, in y3, y4, y5, y6, y7 as well as these two parity checks. But though that evidence is really the union of two pieces of evidence, one coming from the knowledge of y3, y6 and the parity B, check B, and the other coming from knowledge of y5, y6 and the parity, actually it is the union of three pieces of evidence, because you are collecting evidence from this segment here, from this segment here as well as the local information over here. So, you are collecting information, and so what you actually put out then here is the conditional probability given the union of the evidence. So, it is in this sense that I am actually saying that that is what happens in general. So, in general you are passing messages like this, and what do you have to do this? So, the actual message is proportional to these quantities, but you pass messages just the way you would do on the junction tree. You would take the incoming messages, you would take your local kernel and you will form the product. Remember that the message that you are passing is really a vector, because this function you have to pass this function, means you have to pass this quantity as a function of x t. Since x t can take on values either 0 or 1, you are actually passing a vector with 2 components, right. So, that is what happening here. However, we want to now, since the 2 quantities of the vector that you are passing are really probabilities and their sum is 1, it is reasonable to assume that you could get away by just passing a single probability instead of a pair of probabilities. So, it turns out that you can do that, and you can end up by just passing likelihood ratio. So, let me show how that actually works. So, under the GDL, we have that P of x t union I is equal to 1 to dV minus 1 of E I is proportional to the product j is equal to 0 to dV minus 1 P of x t given E j. Now, let me rewrite this by spelling this out for x t equal to 0 and 1. This holds for both x t equal to 0 and 1. If I take the ratio, if I write this quantity for x t equal to 0 and then I write it for x t equal to 1 and divide both sides, then this proportionality sign will go away and I will have equality. So, I can write, so this implies that the probability, now so I have to be a little bit careful here. Now, I can either interpret, so our here I guess in accordance with our earlier notation, these x t's are really belonging to the set plus minus 1. Let me write x t is equal to minus 1 to the u t. So, then u t is either 0 or 1. So, I can instead write this as the probability of, so I can say that probability of x t equals 1 given the union of the E i's divided by the probability of x t equal to minus 1 given the union of the E i's is equal to the product j is equal to 0 to dV minus 1 probability x t equal to 1 given E j divided by the probability x t is equal to 0 given E j. Okay, so this is what you would have. And in terms of if I switch this and were to rewrite this in terms of not the x j's, but rather the u j's, so I would replace these symbols by u this should have been -1, excuse me. So, I can write here -1. So, I can write this instead as u t equal to 0, u t equal to 1, u t equal to 0, u t equal to 1. So, I have switched from u t in terms of u t rather than x t. So, what this is telling you is that here, whereas here we were passing functions where each function was actually a vector, here what we are doing is we are passing a ratio which is a scalar, and now the proportionality sign has also gone away. And what we will actually do is this is the log likelihood, this is the likelihood ratio, we will actually pass on to the log likelihood ratio. So, let us define Lj to be ln of p of u t equal to 0 given E j divided by p of u t equal to 1 given E j. And let us also denote by EDV the union of the evidence okay. So, let us take these two definitions. Then if I call this equation 1, then in the log domain, taking logs on both sides of 1, gives us that you have LDC is the sum I is equal to 0 to dV LDV, sorry, is the sum Li I is equal to 0 to dV minus 1. Okay. So, I just want to reiterate that our messick passing algorithm has in essence remained the same, because what we were doing under the junction tree was we were passing a function where the two quantities were proportional to probabilities. Okay. But you can actually make do, because if your interest is only ultimately our interest is only or rather we can recover the two probabilities even if we have access to only their ratio, because after all we know that the sum of the probabilities is 1. Okay. So, you can make do by sending a single real number as opposed to a pair of real numbers. There is a slight increase in the complexity of the operation that is carried out at the check node. At the variable node, things perhaps even become simpler, because now you have a view that rather than passing these conditional beliefs which we had here, we are now going to have the same diagram, that except that we are actually going to pass we are just going to pass likelihood ratio. So, let me just draw such a graph. So, you have your node which I will still label as x t, and now I will say that what is incoming is the likelihood ratio, which is L1. What is coming from the other nodes is also likelihood ratios based for the same code symbol, except that the evidence on which they are passed is different. and then what you are actually computing is LDV, and you are computing this according to this sum. Okay. So, this is the message passing that is carried out at a variable node. Now, what happens at a check node? At a check node, things are a little bit more complicated. So, in terms of functions, there is no problem, because if we know that if you have, let us say, a check node, C, then what is going to be, you are going to have when we were passing beliefs earlier. So, under the belief messages were quantities. So, this would be proportional. Let us say that at the other end of this there was the variable x1, and let us say that here this corresponds to x dc minus 1, and let us say that this corresponds to x dc. And so, these respective beliefs, so this belief would actually be proportional to p of x1 given some evidence. This would be proportional to p of x dc minus 1 given some evidence, and what the message that is actually going out would then be p of x dc given the union of this evidence. Okay, so now how do we in every instance it is proportional to. So, the question is, how do you actually represent this? I should add a few dots, because you could have some other nodes as well. How do you represent this in terms of the log likelihood domain? Now, we know that if you were to write down an expression, we know that p of x dc given the union of the evidence is proportional to the not sum over x dc of the product j is equal to 1 dc minus 1 p of x j given E j. So, that means that here what is happening is that you are doing message passing, you are taking all the incoming messages, then you are marginalizing. Now, this parity check would typically be associated in the under the GDL to the following set of variables. You would have x1, x2, x dc. So, you might write this node in this format, and now when you see that, you will see that the outgoing message must marginalize with respect to all the other variables except x dc. So, that is what this not sum represents. It means that you are marginalizing or summing over all possible values of the remaining variables. All right. You can turn it into an expression using involving likelihood ratios as follows. This is a little bit of a trick. So, we will sum, we will take this quantity and sum over u dc equal to 0 to 1. Now, I am going to switch to the u's rather than the x's. So, I am going to form this sum, and for reasons that will become clear, and this is going to be proportional to the sum UDC is equal to 0 to 1 minus 1 to the lambda UDC. The sum U1 through UDC minus 1 subject to sigma Uj is equal to UGC. And here you would have so you would have this expression. And now just an observation. So, you are summing over UDC and over all the other random variables, but subject to this condition. So, that means that you can actually replace, see if you replace the UDC term here by the sum of these variables, then you can actually get rid of the sum over UDC. So, this can be rewritten as being proportional to the sum over U1 through UDC of the product j equal to 1 to DC minus 1 minus 1 to the lambda Uj P of Uj given Ej. So, this should pardon me, this should have been Uj. Remember that Xj is minus 1 to the Uj. So, there is no difference between a belief about Xj and the corresponding belief about the belief about the corresponding value of Uj. So, it turns out to be more convenient to deal with the U's rather than the X's. So, that is what I have actually done here. Okay. So, now I am going to actually, so I have a sum here. I am going to take the ratio of this quantity with lambda equal to 1 in the numerator and lambda equal to 0 in the denominator. So, what that will actually give me is that therefore P of UDC equal to 0 given EDC minus P of UDC equal to 1 given EDC divided by the sum P of UDC equal to 0 plus P of UDC equal to 1 given EDC is then the product j is equal to 1 to DC minus 1 Okay. So, I have this sum, and now you can see the connection with log likelihood ratios, because this can be rewritten in terms of log likelihood ratios because I am just going to divide, let us say I am divide this by P of UDC equal to 1. So, I will get the likelihood ratio here minus 1 and similarly over here. So, this can be this again in terms of log likelihood ratios. Reduces to e to the L dc minus 1 upon e to the L dc plus 1 is the product j is equal to 1 to dc minus 1 e to the L j minus 1 upon e to the L j plus 1. So, you get an expression like this, and we just have about a minute to 2 minutes left. So, let me just summarize. So, what I tried to actually do was I was trying to explain to you how belief propagation message passing works on the Tanner graph, and I said really it is something that you already know, because you know it in the setting of the junction tree, and what we do is we just port the algorithm from the junction tree to the Tanner graph, and everything stays the same as long as your neighborhood is tree like, and we saw that. And so you have an interpretation of the messages as beliefs, and now because they are beliefs, it turns out that instead of passing messages you can actually pass log likelihood ratios. We wrote down the expression for the message that is passed across a variable node in terms of log likelihood ratios, and we are just about to do that for a check node. But since we are running out of time, let us continue this. We will continue this part of the discussion next class. So, thank you.